So welcome. So last time we did about the Kepler's laws, and we saw there were three of them, and basically one was the observation that planets go in elliptical orbits, not circular orbits. Now sometimes they're very close to circles. What we have is very close to a circle. Ironically, because an ellipse has a changing radius, it turns out that we are closer to the sun in our winter time than we are in our summertime. So that's not the reason for the seasons. The seasons is because of the tilt of the Earth's spin axis. So we're not very elliptical, but we are still somewhat elliptical. And remember that a circle is a special case of an ellipse. It's not that the ellipse is a special case of a circle. The circle is a special case of the ellipse. And if you see something like a comet, that's very elliptical. And that's an extreme example for us. Okay, and then the next thing was that it's a very difficult thing to figure out, which was that if you take any object like a planet or a comet or whatever, and you could plot its path with time, you'd see that what's constant throughout that journey. We always look for constant things in physics and engineering because we want to do an equation. I mean, that's what enables us to do progress. What's constant is the actual area swept out by an imaginary line from, in this case, the sun to the planet. So the speed's not constant. It's the area that's swept out by this imaginary line that's constant. That's like a weird thing. What it kind of gives you is that when you're further away, you travel slower because the string's a lot longer. And when you're close by the sun, you travel faster because the string's a lot shorter. We kind of get this anyway from energy points of view. If I think of this as not as up the page, down the page, to the left and to the right, think of it as altitude from the sun. This is a very high altitude from the sun. And so this object, when it's here, has a very high potential energy, very large potential energy at that point. I'm sorry, I'm trying to finagle my pen while we're talking. There's a very high potential energy. And so if it's got a very high potential energy when it's out here, it's going to have a relatively low kinetic energy, and so it's got little velocity. And when we're down here, we have much lower altitude, and so we have much less potential energy. And because mechanical energy is conserved when there's no friction, then we must have a very high kinetic energy, meaning a lot of speed. So you can kind of see it intuitively from that. They didn't know anything about that. Energy is one of the weirdest things. Energy took until about 150 years ago to really get sorted out. They didn't get energy. Energy is kind of like, it's quite bizarre. It's something which is passed from one object to another, although you can't really measure it in terms of, it doesn't change the mass, it just changes the way it behaves. It's quite an elusive thing. And so they didn't know about energy, they just knew about what they could see. And then he went even further, and it took him about 10 years to get to this, but basically he eventually got to, he could link the period of an orbit to the distance of the semi-major axis in an ellipse, and we think of that as the average radius. So, and if we're working in, the one wrinkle is if we're working in meters and seconds, then K is a wacky number. If we're working in Earth years and astronomical units, then K is equal to 1, because we go around the sun one time in our year, and we're one astronomical unit from the sun. So if I ask you a question about this, I would ask you a question about this in terms of Earth years, and we did this last time. Earth years and astronomical units. We got to this, and this is a little bit out. So consider the solar system. Which planet has the longest year? Well, if you think about it, we just decided that you travel slower when you're further away. because you're at higher altitude, so you're traveling slower, and you're going around a bigger, we call it a circle, it's a nearly circular ellipse, but you're going around a bigger circle. If you're traveling slower and going around a bigger circle, you're going to take a lot longer to go around the sun than if you were nearby and traveling faster. So which planet has the longest year? Well, a year is how long it takes to go around, so D must have the longest year. And I think we said for Neptune last time that the Neptune's year was like something like 130 years or 150 years or something like that. Whereas for us it's 1 year. And if you go to Venus, it's, you know, a few months to go around. So which planet is moving with greatest speed? And what we said was because of this kinetic energy, potential energy change, I tend to think of it in terms of that. Because of that, I can tell you that which planet is moving with the greatest speed? Well, A will move with the greatest speed. It is not so high, and it's going on a small orbit. And then which planet has the longest orbital period? Orbital period is just a bit of test on language here. Orbital period is how long it takes you to go around once, which is the same as the year. So we'd end up with D is the longest orbital period. So there's a bit of terminology there. Okay. Then along came Newton. And Newton basically, just to set this up a little bit, so Newton was a frighteningly bright person. He was the son of a Lincolnshire farmer. The father died, the mother remarried, the stepfather did not want kids. And so basically he got his new wife to move out into the city with him. Meanwhile, Newton was left on the farm, basically raised by, you know, they were not incredibly well-to-do, but there were farm hands and stuff like that. There were people who worked for them. So he was basically left on the family farm. So, just when at some point they decided to move back to the farm, they shipped him off to school. So, and that was been put with a family that had a teacher. The way that teachers would earn their livings, there wasn't really schools at that time, so basically they'd opened their households up to kids of the better off, and they'd come and live with them, like a pre-boarding school. You went to live with the family. So he was really smart, and he got into Cambridge. Cambridge is, you know, at that time there was probably only a few universities, and certainly it was one of the centres of learning in the entire nation. And there was a couple of ways you could get in. And one way was you were rich, so your parents would pay for you to go to Cambridge. And the other way is that you were poor but really smart. And what they'd do is they'd take you on. The colleges would take you on because they had a vested interest in getting smart people there. And they'd kind of give you a job to do. So part of his job was doing stuff for the richer students. I mean, it was basically... And that actually is funny, not to be critical, but that kind of, to some extent, that goes on till certainly when I was a student. When I was a student, the colleges in Cambridge had set-asides. These were places that were reserved for pupils from private schools. And like, you know, one school would say, we have 10 seats in Magdalen College. And basically, you know, they'd pick, well, the college would pick, but they'd have those set aside for kids from that school. So, but there was always this, certainly in my day, there was always this thing about if you're really smart, you could still get in on a scholarship. You didn't have to do jobs for people in my day, you got in on a scholarship. But it was just like a weird kind of situation where, you know, it was kind of like, you're rich, you get in, you're poor and bright, you get in, you know, and you rub shoulders with each other. It's kind of interesting. He was so smart that when he got to graduating, one of the math professors retired and said, you need to hire this guy to replace me. So he got hired to a job which is still in existence today. Can you imagine that? That job is still in existence today. It's been passed down from person to person over 350 years. Stephen Hawkins has that job today. They're like the same title, the same pot of money and all that kind of stuff. It's kind of very, very interesting. And he was smart. He was really smart. He did 10 years of physics. He did 10 years of alchemy. And he did 10 years of communing with the spirits. That's what he spent his time doing. Alchemy didn't work out so well. It's kind of like, he had the basic idea, you can transmute lead into gold. It's just not with the ways that he was doing. You can't do it chemically. You've got to do it using nuclear effects. And what you end up with is really, 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 really expensive gold. I mean, so it's not worth it, you know. But you can do it. But not the ways that he was trying. He was very, you know, if ever you want to be famous, be really careful. Because I've never heard of famous people who did not pay a heck of a price in terms of the rest of their life. My wife says it's sour grapes. I like to read these autobiographies or these biographies of really famous people, and I'm always chuckling to myself, saying, "Oh man, this guy was really messed up," you know. But it's true. In most cases, they really had a burden. And I think it's in part that you can't get to the stage where you do something that's going to be talked about 350 years later without being completely obsessed by it. There was I saw a program once, and this guy was trying to talk about the difference between being really, really bright and a genius. And he said that he thinks it's like when you're really, really bright, if you're working on, you know, a really important thing, and somebody comes in and says, you got to come now, your mother's really sick, they'll put down the pen and just leave, you know. But for a genius, if they say, you got to come now, your mother's really sick, they'll say, just a minute, and they'll have to finish off that thing, because nothing comes between them and what they're on. And he was certainly, I think, like that. He used to go down to the refectory, the cafe. He'd go down there at the end of lunch and the end of dinner and pick up a meal and take it back to his room. He did not want to socialize with people. Did 10 years brilliant work on physics. He looked up to a guy called Robert Hooke, and poor old Hooke was, well, good old Hooke was one of the motivating people behind the Royal Society, which was, they got money from the Crown to set up this club which printed papers, which distributed them, rather than just you writing to your friends. You submit it. If it's deemed good enough, they print it and they just send it out to the community of scientists. It's the scientific way, at the very beginning of the scientific way. And the idea was to make sure that it just wasn't nonsense, it'd be peer reviewed. That's the beginning of peer review, which is a huge thing about that. When you hear that science is a club and all that kind of stuff, be really wary of it. Science is very cutthroat. There are powerful people who can, just by dint of personality, shout people down. There's always personality. But there's always people ambitious enough to challenge them. And so if you say something that's important and wrong, you can say stuff that's wrong and not important, and no one cares. No one's going to say anything. But if you say something important that's wrong, people will challenge you on it. They'll do the work. Because if they can prove you wrong and you're powerful, that brings them up quite a bit. So this idea about science being either a club that kind of like just colludes, or this really polite society where, oh, thank you for your input, I will take that into account the next time. No, it's very personal. It's like, you're an idiot. Why are you saying this to me? You know, you clearly don't know basic physics. I mean, it's insulting. It's, you know, I mean, English people especially, I think. I've been at a few conferences where there's been a fair number of English people there, and you know, they're not above being quite rude, actually. So And this is the beginning of it. The idea is you put your work forward, it gets looked at by anonymous peers, not just peers, but anonymous peers who can say what they like about it. And it hurts. I mean, I can tell you, I've had a paper rejected out of hand. And it was like, man, that's a decent paper. I'm ticked off by this, you know. That's why it's anonymous, so it doesn't get personal. He was encouraged to do this by Hooke. He went and Newton put some papers in. They were rejected. They were rejected by old guys like me who'd never actually done any research in their lives, who just knew what Aristotle told them, basically, and dismissed it out of hand because of, you know, the status quo. Whereas Newton was doing research. Newton was in his little room playing with things. And so he was burned. And that's why Newton did not publish again in the Royal Society and published books. Newton published a book on mechanics and a book on optics, and they were tomes. It was like, here's my, 5 years work on mechanics. Argue with that, I'm not just going to put a little bit in and let you just argue with it. You're going to argue with my entire book. And magnificent books. Not all right. Quite a lot wrong in them. But really seminal books. Really, really major books. He also, because of that, developed a complete hatred of Hooke. Your hero leads you astray and you really resent it. So there's this battle between these two guys. And Hooke keeps trying to put out the hand of, friendship. And Newton kind of is I think determined for revenge. There's a famous statement by Newton that, Hooke sends him a letter saying, look, I know things didn't go so well at the beginning, but, we really do appreciate what you're doing. This is amazing. And it'd be so good if you shared it with the community, And Newton writes back saying, oh, thank you ever so much. If I have the ability to see further than others, it's just because I was able to stand on the shoulder of giants, Like, it's not me, it's all the people before me, Galileo. Didn't say that, but that's. It also is significant that Newton, was a very tall person. And Hooke was a very short person. And so there's this rub of, he's turned around to a short person and saying, if I can see further than others, it's because I stand on the shoulders of tall people. It's kind of like a little dig, So Newton did that. 1666, Black Death in Britain. Plague came in. Why was plague so bad in Britain? It was bad in Europe, but it was really bad in Britain. Why was it so bad? It was so bad in Britain because we'd just gone through this panic about witches. And as you know, witches are usually female and usually have cats. So we got to look out for wacky females who have a cat, and then we'll test them. You put them in the river, and if they sink, they were innocent, and if they float, they're a witch, and you burn them. It's like. And it was really bad. People. We can look back now, and it is quite funny. But real people, were tormented during that time. It just goes to show, again, getting on my science horse. There's no evidence to say that females with cats can cast spells on people. Evidence-based is it's not there. And yeah, it's easy to turn around and say, oh yeah, I got this bad pain in my leg when I walked by their house. It must be them, So, bad times for cats. Turns out cats fulfill a really wonderful function in that they keep rodents down. To this day, in Britain, you don't have fleas and you don't have rabies actually, so you just let your cats out. My cat used to go out all the time, scratch on the door to come in, scratch on the door to go out. Would occasionally bring presents back, field mice. It used to put field mice in my Uncle George's slippers. He'd put his feet in. the mouse there and stick it out. Not so long ago, maybe 20 years ago, some people at one of the universities in Britain did this survey. They asked people to save the field mice that the cats brought back. And they studied what kind of field mice, what the species were, and also how many of them. And it turned out the cats in Britain in like the 90s were killing, millions upon millions of rodents and keeping the rodent population down. Okay, you go through a few years of killing off all the cats you can find, then you've not got that, so the rodent population went through the roof. And then along comes a few, I've heard people say this is not true actually, but the story is that along came some plague-carrying rodents from Europe, and then you got no mice to keep those down. So what happens, it spreads like crazy. And in Britain, about that time, 1 in 3 people died. So imagine you've got a village of 100 people and 30 of them just die within a couple of years. It's devastating. Where they've got people away from centres of population, so they try to send them to the countryside, send them away. So Cambridge was closed down. Newton's in his farm again, and the story has it, he sat under an apple tree and the apple fell on his head and he thought gravity, and it's like, yeah. What Newton was really thinking was, according to Aristotle, the rules in the heavens are completely different from the rules on earth. I mean, you think about it, the moon's up there, the stars are up there, they never fall down. They go around us, but they never fall down. So everything else falls down. So there must be different rules. And they invented, that's what Aristotle did, he invented things about what that all was. At some point, I don't know if it was Aristotle, but at some point they decided that heaven was 80 miles up in the air, and all the stars were bits of light leaking out as your ancestors looked back to see how you were doing. They open a window and there's a star there, that kind of stuff. Newton said, physics is physics. What happens down here happens up there. The force that pulls the apple from the tree is the same force type, not the same size, the same force type that pulls on the moon. Why is the moon not falling to the earth? And he started figuring out about, it's because it's going sideways. And in the time it takes to fall by a certain amount, the earth is curved by a certain amount in the time it takes. So he's figuring out orbits. He's figuring out satellite motion by saying the fundamental physics is the same all over the universe. And to this day, we believe that. The fundamental physics is the same all over the universe. Because if you don't, then you can't really say much about stuff. So in a way, you've got to assume that what happens over there is the same what happens over here, or else I can't talk about over there unless I go there. And I certainly can't go into the heavens. So Newton had this, because he was an intellectual person and he didn't need that much equipment. He had a little room at Cambridge. I'm sure he had a little room at his house in Grantham in Lincolnshire. So he basically, business as usual, and he's writing his books. So for him, it wasn't, I suspect for him, they kept paying him. So I suspect for him, he had a great time, it was great. Anyway, so all this gets distilled into his book on mechanics, and there's a whole other book on optics. And as you'll see in physics too, there are diagrams that Newton drew which are in the physics books to this day. It's like I don't know if it's like honoring him. There's a language that he used, which is exactly the same as the language that's in your book today. The guy was amazing. Right at the very end of his life, he'd done physics, he'd done alchemy with not so much success, and he did communing with spirits, I don't think he had any, that's my sense, he didn't have any success with that. Madame Curie also spent time looking at that. It's interesting, just interesting side of things. So right at the very end of his life, he became quite famous. He became more outgoing. I think it's partly, I'm getting old, and what happens is you get older, your frontal lobe starts closing down. So you find you're saying less than, you've been more and more daring. So it may be that that's what happened to him, but he became quite the socialite very late in life and was employed as the master of the Royal Mint. And they were having a problem because coins were gold and people would nibble away at the gold coin. So it says one sovereign on it, but half of it's missing. And that gold's been sold. So it's like you just take a nibble off the edge of all your coins and all that. That's one of the reasons why you have serrated edged coins. Is a tradition from that day. If it's serrated edged and someone's nibbled at it, you can easily see the serration and say, I'm not taking that coin. But if it's just a round thing, then what, is it still perfectly round, and he basically found they were introducing money, notes, or not notes, but coins that weren't worth their set value. And he found some forgers. And so sometimes it's claimed that he was the first detective. I don't know how true that is. So a very interesting person. There's a really good book on Newton, which I'll dig out the name of and I'll bring it back to you. It's fascinating to read about these people. So what did he do? And, of course, we could not possibly do it. And my sense is, I want you to, certainly in terms of making up equations, it's something that you will do in your career. So what we have is, we have a situation. We have an object, call it the earth. We have an object, call it an apple. And there's forces between them. So all right, for every action force and equal opposite reaction force, that's good old Newton. So we're not going to jump into the very beginning. He knows about forces. And basically what he says is the force of the apple on the earth is the same as the force of the earth on the apple. And then he says, well, okay, imagine that I make the apple twice as big. I get twice as much force. We know that from day-to-day life. Big apple weighs more than a small apple. By analogy, if I made the earth twice as big, do I expect twice as big a force? I think so too. If the earth's twice as big, it's the earth that's doing the pulling. So, yeah, twice as much earth means twice as much force. So first thing you do when you're doing equations is you write, I'm going to find a place to write this down. You basically make a list. So I want the force due to gravity, and I know it depends on the mass of the earth and the mass of the apple. And if, when the mass of the earth is increased, the force increases, put the mass of the earth on top. And if, when the mass of the apple is increased, the force increases, put the mass of the apple on top. And then you say, well, what else could this be due to? And you say, well, the separation, of course. Now, if you go from low apple to high apple, you don't see any change. So now he's doing something that's really quite remarkable. He's picturing what this gravity thing is. And he's saying to himself, sorry, that's from you guys actually. So what he's saying to himself is, so here's the earth, and there's this thing called gravity which emanates from the earth. And so there's this thing called gravity which is kind of like emanating through that surface area. And then as you go higher, that same amount of gravity is emanating through that sphere, that surface area. And now we have, and can you see as I go further away, my little dashes are more spread out. There's less intensity to my dashes. And that's what he envisaged with this gravity thing. Whatever it is, it gets diluted, if you like. It gets reduced in intensity as you go further and further away, because you've got to have the same effect on an apple at this side as you do on that side. It's not like the earth looks at the apple and says, oh, I'm going to focus on you. It's just saying, I'm here, and I don't care if there's an apple there or not. I'm going to have my gravitational effect. And so he recognized that this gravitational effect is having to spread out over a surface of a sphere, which is 4 pi r squared. And so we get this r squared relationship. So the intensity is going to be proportional to 1 over 4 pi r squared. And so what he realized was it's not just that as you get further away from the Earth, the pull of gravity gets less. But as you go further away from the Earth, the pull of gravity gets less by an inverse square law. Because there's a spherical symmetry. And any time there's a spherical symmetry, it will fall off, whatever it is, by a 1 over 4 pi, 1 over r squared. So light intensity falls off the same way. If I double my distance from the lamp, I get not half, but 1/4 the intensity. If I triple my distance from the lamp, I get not 1/3, but 1/9 the intensity. If I 5 times my distance from the lamp, I get not 1/5, but 1/25 of the intensity. Same goes with sound. Same goes with radiation. You never knew about radiation. Same goes with electrostatic forces. When there's a spherical symmetry, you get this inverse square relationship. What's the alternative? The alternative would be if I had some kind of thing where the effect spread out like a cylinder. Then that might not be an inverse square relationship. You can imagine different symmetries. So what Newton did was, and this was, amazing, was he was able to, let's see if I get the right place back. Yes. So, I'm sorry. Yes. Oh, there we are. So he was able to cancel that. You got to let me cancel that. Come on. Jump back in. I'm sorry. So let's go to. I'm in a mess now, aren't I? So he was able to. So he was able to put this together and get that, this must be a 1 over r squared relationship. Now, what I'm saying to you is that methodology, what does anything else affect this? Absolutely not. Temperature doesn't affect it. So I've got my 3 parameters, m, big M, little m, and r. And because of symmetry, I know it's 1 over r, and I know it's 1 over r squared. That's from symmetry. And then the G is a fudge factor. This equation will work whether I'm working in inches and feet, or pounds, or grams and centimeters. It's got to work. And so how do you make the equation work numerically? You put a fudge factor in. That's what that G is. And sometimes the fudge factor is 1 and you don't see it by chance. But often the fudge factor is not 1 and you see it. And it's got different units in different systems. Now we tend to work with SI, so we tend to see the same units, constant units. But if you go to another system, it would have different units. But there would be a fudge factor there. And he had no idea how big G was. He just knew that we need a G there kind of thing. And so we end up with this relationship, that the force is equal to some constant times the big mass times the little mass over the separation squared. And that's the magnitude of the force. And I'd like you to get to the idea that although, I could not have figured that out, in my life I can figure out equations. Because in your career as engineers, you're going to design systems and you're going to need an overall equation that sorts out the behavior. You do this, you do that, you get this. And you're writing equations. It's not magic. It's not something that's beyond you. It's just the fact that writing an equation on something that's this important, you've got to be in the right place at the right time with the right skills. And this person was at the right place at the right time with the right skills. You might do a similar mathematical thing, a similar intellectual thing on a widget that gets sold to some, game company. And people use it, and you've gone through that same intellectual process, but it's just not going to be famous. But it's the same scale. Fair bit after people started thinking about the vector form of this, because these things are forces, so they have directions. So what is the vector force? And what we do is we say, all right, we're gonna basically have to have a direction on this. And so what we do is, rather than messing with the magnitude, we write it in a form where the magnitude is the magnitude, and we have a thing here, and this looks complicated, but it's just a little unit vector that points in the right direction. And a unit vector has a magnitude of 1, so it's pointing in the right direction. So we've not changed the size of this thing, we just changed the we just added a directionality to it. So this is the magnitude form of this relationship, and this is the vector form of this relationship. There's a negative sign in there. Why is that negative sign in there? It is because when you are interested in the force going in this direction and your unit vector is in that direction, they must be in opposite directions. If my unit vector is there, let's get it the right way round, but the force I'm interested in is there, can you see how they point in the opposite direction? And how do you make the vector point in the opposite direction? You just change the sign on all the components. Now, and the other reason why I put this in as this example is because the book has a negative sign in there. And the book has a negative sign because it says F12 is equal to, and it gives you this thing that's tempting to learn. And people invariably get the sign wrong. And the reason they get the sign wrong is because they're relying on some mathematical hocus pocus to get the sign right. The way you get the sign right is you look at your diagram, okay? And, you know, you will get a question like this, and I will be at pains to look at your signs. Do you have the right direction or not? And that will be worth some credit, because you've got to get it right. And my advice is, forget the negative or not negative. Look at your diagram, and you'll be able to figure out, if you practice your vectors, you'll be able to figure out whether there should be a negative sign there or not. Okay, so this is gravitational force. Cavendish, years later, this was about 1666, 1798. Cavendish measured the gravitational constant in 1798. Two light spheres were put in proximity to two heavy spheres, and there was some kind of fiber holding the two light spheres. And so when they became close, what they did was they moved the heavy spheres until they were somewhat close to the light spheres. And because of the gravitational pull, you felt a gravitational pull which tended to cause this wire to change slightly, this torsion which twisted the wire. And by using a kind of light needle, they'd send a light beam in onto a mirror, and they'd see the image of that light beam would move across a wall. It's like having a meter which is as big as a room. You know, imagine an amp meter that's as big as a room, so a little bit of change you can see. It's like having that, but it's as big as a room. And he was able to measure the gravitational constant. I don't feel a measurable force on me when I walk past the desk, although there is a force on me. So imagine the skill that must have gone into building that piece of apparatus. He made an apparatus which in a room was able to measure the force of gravity between two objects that were right on the surface of the earth. I mean, this is a phenomenal piece of work. The people in about these times, 1798 and, 16th century, 17th century, became really good at, especially the 18th century, got really good at mechanics. They were the masters of mechanical inventions, high precision mechanics. In the 20th century, or the 19th century, 20th century, it became much more, 20th century for sure, became much more electrical measurements and electronics. So now a lot of things that before were done mechanically, now we just do using electronics. So the skill set has changed. These guys were amazing masters of mechanics. Let's do a few of these. Mass A is 12 kilograms and mass B is 1 kilogram. So mass A, mass B, big M, little m, it's just words. So I have a 12 kilogram and I have a 1 kilogram. The masses are located in deep space, so we don't need to worry about the Earth, with a separation of 2 meters. So that's 2 meters. What is the magnitude of the force does the 12 kilogram mass exert on the 1 kilogram mass? Oh yeah, I'm kind of confusing you now because I'm implying there's a different answer for the 1 kilogram mass on the 12 kilogram mass. But in terms of magnitude, they're both the same. Forces come in pairs, mediated between two objects. The forces are equal and opposite, equal in magnitude and opposite in direction. So I know that Fg is equal to big G, big M, little m over r squared, which equals big G. Big G is, can I remember it? Big G is 6.7 times 10 to the minus 11 stuff. 6.7 times 10 to the minus 11. So I'm going to go, so this equals 6.7, let's call it 7 times 10 to the minus 11. That is an issue with some of the homework. Sometimes I call it 7, sometimes I call it 6.7. So sometimes the answers are a little bit out. Just bear with me on that. And then M is, well, big M is 12. Little m is 1. And then this is over r squared, which is 2 squared. So that's going to be 12 over 4 is 3. 21, I don't even need my calculator. 21 times 10 to the minus 11. Is it on there? No, it's not. Let's do that again then. 2 2s are 4. 2 2s are 4. I've got that right. 2 2s are 4. Oh, because I said 6.7. Is that right? Is that where my problem is? 6.7 times 3 is equal to 20.1. That's not on there either. Oh, it is. No, I'm sorry. It's there, that guy. And what I've written down here is 3g times n. So in this case, I said work out everything. So you work g into your problem, and you get 20 times 10 to the minus 11 newtons. But for a test, I would far sooner that you got on with the next problem. So for a test, it would be all right to put down Fg is equal to, well, this bit is 3g newtons, where g stands for 6.7 times 10 to the minus 11. That way you don't have to remember what g is, and I don't have to tell you, and all that kind of stuff. In homeworks, I'll often ask you to do it, working the number out, in part because, I don't know how successful this is, but in part because I want you to get a sense for how big or small something is. Look at this. This is 12 kilograms. That's 24 bag. That's 24-pound bag, basically. And this is a bag of sugar. So I have basically a bag of dog food and a bag of sugar 2 meters away from each other in space. And the pull they feel is 200 nanonewtons. That's like nothing. And you think there'd be a bit more. 2 meters is not that far. Yeah, I think that they'd go like boom, you know. But 200 nanonewtons, not much acceleration. 200 nanonewtons applied to that is not much acceleration. It's not going to take, in fact, you can do it as an exercise. You can figure out how long it takes for them to collide. It's going to be a long time. So, gravity is an incredibly weak force. If you could, so we have all these atoms in the earth and all these atoms in me. If I were to simply charge every one of those atoms, so that rather than having a gravitational force, I had an electrostatic force. So every atom, just take one electron away. everyone in mind take one electron away. I would be a grease smear over the surface of the Earth. It would pull me so hard that I would lose my structure and I would become an oil slick, kind of like over the surface of the Earth. Electrostatic forces are by far much stronger than gravitational forces are. By far much stronger. And then here's a conceptual question. What magnitude of force does the 1 kilogram mass exert on the 12 kilogram mass? And, you know, Newton's third law. And that's going to be 20 times 10 to the minus 11 newtons in the opposite direction. Cool. Cool. Yeah. Okay. Mass A is 18, mass B is 2, displacement vector R. So next level of complexity. Now I want to know what the vector force or force vector is. So now I say, okay, I have 18 kilograms and I have 2 kilograms. And the displacement vector which points from A to B, that's important. The direction, it has a direction. So that direction R is equal to 2I plus 3J plus 4K. That's meters. And now you've got to say, well, what am I being asked for? Well, what is the expression for the vector force experienced by B? I want that. F. Not the force on the 18. I'm asking for the force on the 2, and I know it's an attractive force. In electrostatics, it could be repulsive, but in this case, it's an attractive force. So my first question to you is F pointing in the same direction as R, or is it in the opposite direction to R? If it's pointing in the opposite direction to R, then I have to take that difference into account in my expression. Either way, I've got to take into account. I've got to recognize I'm opposite. I'm not the same as I'm opposite. That affects your signs. So what do? I write down my expression. I say FG vector is equal to big G, big M, little m over R squared. There's my magnitude. And I multiply it by this R hat. R hat is the symbol for the unit vector. Now, I get a choice for, well, let's do the first bit first, and then we'll get to it. So FG is equal to, when it says write an expression for, and I will use that on the test, write an expression for, it means you don't have to work the numbers out, you just have to put them in the right place. Why? Because if I can see that you're putting the numbers in the right place, I can easily see, do you know what you are doing? And if you don't know what you're doing, I can easily see that you don't know what you're doing and why, what mistake you're making. If I ask you to give me a number at the end, be it I, J, K, or whatever, I can't tell what you did very often. And so when I say write an expression for, I mean you can leave the skeleton out. Just put the numbers in. So this would be, G. Rather than big M, I'm going to put down 18. Rather than little m, I'm going to put down 2 over. Ow, I have a bit of a problem here. I've got to figure out what this R is. What is my separation? So R is equal to, how am I going to find my separation between these two masses? I give you the displacement vector. How can I get the actual size of that gap? What do I do? Pardon? What is it? Who did this? Magnitude. And whose law do we use? Whose mathematical thing do we use to get that? Pythagoras. Pythagoras in 3 dimensions. So it's going to be that equals the square root. And we go, well, that's going to be 2 squared plus 3 squared plus 4 squared in this case. And in principle, you can say that this is going to be the square root of 2 squared plus 3 squared plus 4 squared. Now that is squared, of course, isn't it? So that would be squared. So I did that bit. Again, I'm writing the expression for. I'm going to multiply it by my unit vector, but my unit vector has to be expressed in ijk. So now I have a decision to make. I have not drawn my unit vector on my diagram. It's my decision where I draw it. I'm going to draw it along this line, but shall I draw it from the 18 pointing towards the 2 or from the 2 pointing towards the 18? I need a vector, a unit vector that's along that line. And there's two choices I can make. One is I make my unit vector point in the same direction as my force, which in this case is the opposite direction to my displacement vector. Or what I do is I put it in the same direction as my displacement vector, in which case in the opposite direction of the force. I prefer to do it in the same direction as my displacement vector. That's my preference, just my habit. So my unit vector will be, well, it's in the same direction as this, so it's going to be 2i plus 3j plus 4k, oops, k, divided by. Now, the problem with this unit vector is it's too big. It is not 1 unit long. It is the square root of 2 squared plus 3 squared plus 4 squared unit long. So my unit vector would equal my vector, let's call that a vector so I know that's a vector, over the mag, which equals 2i plus 3j plus 4k over the square root of 2 squared plus 3 squared plus 4 squared. So I can write up here, it's going to be over the square root of 2 squared plus 3 squared plus 4 squared. So now I made that into a unit vector. But is that pointing in the same direction as my force that I want, or is it pointing in the opposite direction? Here's my unit vector. That's what I just wrote down. That is that. Is it pointing in the same direction as this force, or is it opposite? Opposite. So in this case, I might want to put a negative sign there. Or, if I don't want to put a negative sign there, I can make this minus 2i minus 3j minus 4k. Or, I could decide to have my unit vector pointing in the other direction and call it minus 2i minus 3j minus 4k from the very beginning. You know. Can you see how it's the diagram that informs your math? Now, if you want, because this is going to happen, people are going to turn and say, oh man, let me just clean this up a bit. So people are going to go, that's going to be minus 2/8, going to be 36g over, that's going to be 4, 9 makes 13, 29, 35, is that right? 4 4s are 16, 25, 29. Square root of 29 squared is 29. 2i plus 3j plus 4k over the square root of 29. Forgot one thing. What's that one thing? What did I forget to put in my answer? Newtons, yeah. Even though you got all those IJKs flying around, you've got to have units. This is going to keep coming up. Physics 2, we do this a lot because we talk about electric forces, electric fields, magnetic forces, magnetic fields. It just keeps going on. So this is something to master now. You get the benefit from this in the test, and you get the benefit from then on. So this is a skill, you know. Last time we did Young's modulus, it'll come up once. This is going to keep coming up. So just make sure you're on top of it. And what I'm going to do is, so questions on this. Really important. Questions on that. Good. Okay. I'm going to stop there.